Hi all, welcome to another video of electrical machine design. And in the last video we have discussed the synchronous machines and its theories. So today we are going to discuss the problems of synchronous machines. So it will be in two parts. So here we are discussing the part 1. So the first problem is determine a suitable number of slots and conductors per slot for the stator winding of a 3-phase 3300 volt 50 Hz 300 rpm alternator. The diameter is 2.3 meter and the axial length of core is 0.35 meter. The maximum flux density in the air gap should be approximately 0.9 Weber per meter square. So assume sinusoidal flux distribution and use singular winding and star connection for stator. So these are the given values, and based on the values we have to determine the number of slots and conductors per slot. Okay, the main dimensions capital D and the length of the core capital L are already given. Okay, so the first step is to write down the given points. And here the frequency F, we know it is 50 Hz, and the voltage it is 3300 volt, and RPM it is in rotation per minute, so it is capital ns 300. If it is small ns, that is rotation per second, so we have to divide that 300 by 60 for making it into rotation per second small ns. And the diameter D is given, it is 2.3, and L is given as 0.35, and the maximum flux density in the air gap. Okay, maximum flux density in the air gap is given as 0.9 Weber per meter square, that is Bm. It is given as 0.9 Weber per meter square. Okay, so these are the given values. And first, actually, while we are doing a problem, we must know the equations. Okay, we must know the final equations. That is, here we have to find the number of slots and conductors per slot. Okay, number of slots and conductors per slot. So normally the number of slots and conductors per slot are determined by the knowledge of T phase, that is T turns per phase, T phase. Okay, and the equation for T phase will be E phase divided by 4.44 F5 kW. Okay, so this is the actual equation for T phase. So after finding the turns per phase, we can simply find the conductors, total number of conductors and conductors per slot, likewise. Okay, so for that we have to find the unknown values of this equation, and step by step procedure we are going to find that unknown values. So the first one is the synchronous speed. Here it is found that synchronous speed in RPS, it is ns. Okay, so ns we know it is the equation of capital ns by 60, that is 300 by 60, and we are getting it as 5 rps. Okay, and for finding the number of poles, okay, for finding the number of poles P, we are using the equation as 2f by ns. Okay, P is equal to 2f by ns, or we can use normal synchronous speed equation, that is we know it is ns is equal to 120 f by p. This ns is given, this f is given, from that we can find the p. Okay, p will be equal to 120 f by ns, 120 f by ns. So this is the equation of p. Okay, so we can use any equation for finding the number of poles p. So here we are getting it as 20. Okay, and then we have to find the average flux density, that is BAV. Actually it is the specific magnetic loading, here BAV. Okay, BAV. So in the question, the point is that assume sinusoidal flux distribution. Sinusoidal flux distribution. Okay, sinusoidal flux distribution means actually it is having a sinusoidal structure. The flux density waveform is having a sinusoidal structure. Okay, and 0, pi, 2 pi like that, and this one is the maximum value of flux density Bm. Okay, so from this waveform we can simply calculate the average flux density. B average is equal to, okay, it will be equal to 2 bm by pi, 2 bm by pi. Okay, that is we learned how to find the average value of some waves. Okay, different AC waves and different square waves like that. Okay, so if you are going to find the average value of a sine wave, okay, sine wave for a single cycle, that is for a positive cycle, actually that we average will be equal to 2 vm by pi, 2 vm by pi. So likewise here the B average will be equal to 2 bm by pi. Okay, so I hope it's clear. So likewise we are finding the value of BAV. BAV is equal to 2 bm. Okay, 2 into bm by pi. Okay, so in the question already the maximum flux density is given. Maximum flux density is given, not the average flux density. So don't make a mistake by taking that maximum flux density as BAV. Okay, so it is wrong. So be careful while we are denoting the notations. Okay, so it is bm by pi, bm by pi. So the flux density, okay, B average is given as, we are just finding it as 0.574. Okay, and after that using that BAV, that is the equation for BAV, we know it is BAV is equal to P5 by pi dl. Okay, P5 by pi dl, and here the value of flux can be found by multiplying that BAV into pi dl, okay, by P. Okay, so just we are substituting the values for BAV. BAV it is 0.574 and pi dl. D is given, it is 2.3. L is given, it is 0.35, and P we have just found P as 20. Okay, and we are getting the flux per pole as 72.5 10 ratio minus 3. Okay, and after that we have to find the phase voltage E phase. Here it is given that in the question it is given that the use single layer winding and star connection for stator, star connection. So in the case of a star connection, we know that V phase equal to VL by root 3. So likewise E phase equal to EL by root 3. That is normally the value of voltage given will be the line value. Okay, so here it is 3300 volt. So E phase equal to 3300 by root 3. We are getting it as 1910 volt. And next one, we are going to find the T phase equation. Okay, T phase, so T phase equal to E phase by 4.44 F5 kW. Okay, we have found the value of E phase, we have found the value of phi, and we know the value of kW. Okay, etc. So here the turns per phase. Okay, T phase is found as 124, and here if the value of kW, okay, kW is not given, so we can assume the value of kW as 0.955. Okay, so this is the correct value of assumption for kW winding factor. So if by substituting that values in T phase equation, we are finding the T phase equation for the value of T phase as 124. And then for calculating the slots, okay, T phase is 124, and for calculating the slots we have to consider the slot pitch. Okay, slot pitch. So in the previous video we just learned the slot pitch. There are three categories for slot pitch. Okay, So here the voltage rating is, it is 3300 volt, so it is 3.3 kV. So actually the value is less than 6 kV. Okay, the value is less than 6 kV. So for voltage up to this 6 kV, uh, the value of stator slot pitch, okay, that is the YSS, is 40 mm. It is 40 mm. Okay, so we know that the equation for YSS is pi d by number of stator slots. So the number of stator slots SS will be equal to pi d by YSS. So the value of d we know, okay, and the value of YSS we know, that is stator slot pitch is 40 mm. Okay, and using we can find the stator slots. Okay, or we can another method. Okay, and after finding these stator slots, we have to find the value of Q, that is slots per pole per phase. If we are finding the number of slots per pole we have to find, and after that slots per pole per phase we have to find. Okay, or we can use an equation like this, that is small letter q. Okay, slots per pole per phase is small letter q. So the small letter q can be found using the equation pi d by 3 into pyss. Okay, pi d by 3 into pyss. So here the value of d we know, and the value of p, number of poles we know, and the value of YSS, stator slot pitch, is 40 mm we know. Okay, and here all the values are in millimeter. We are taking all the values are in millimeter. So utmost care needed there, because sometimes we may be wrongly choose a parameter. Okay, that is the millimeter parameter in the numerator and a meter parameter in the denominator. Okay, so that is wrong, the unit is not correct. So here the d is in millimeter, it is 230 millimeter, and 3 into p we found it is 20, and YSS it is 40 mm. So in this case the value of d, okay, here the value of d we know it is 2.3 meter, and we are taking it as 230 centimeter. Okay, that you can see here, and the stator slot pitch it is 40 mm, which means it is 4 centimeter. Okay, that also you can see here. So by doing that calculation we are getting the value of q as 3, and next step is to find the number of stator slots. Okay, the number of stator slots. So in the previous step, that is if you are using the equation, that is YSS equal to pi d by SS, we will be finding the stator slots directly. Okay, or if we are using this equation, after that we have to find the stator slots as 3 into PQ. Okay, 3 into PQ, that is in the previous case Q, that is slots per pole per phase, it is given as 3. Okay, so here the poles we know it is 20, phase we know it is 3. Okay, so by substituting that values here, we are getting the stator slots. Okay, stator slots as S is equal to 3 into 20 into 3, it is equal to 180. Okay, and the total number of stator conductors. Okay, stator conductors we can find using the equation 6 into T phase. Okay, so here the total T phase is 124. So if we are multiplying that value with 6, we are getting the total number of conductors, it is 744, and therefore the conductors per slot ZS is equal to total number of conductors by total number of slots. So 744 by 180. So we are getting approximately as 4. Okay, which means we can accommodate 4 conductors in a slot. Okay, So that's about that question. Okay, I hope it's clear. So individually do the problem, do the calculations. Okay, uh, I hope all the equations and all the calculations you understand well. So thank you.